Okay, so we are going to cover quite a few examples that will help us with our first labs on speed and acceleration. It'll kind of give us some reasoning for some of the data that we get. So we need to have some terms that we understand first. And these are terms you probably use in your everyday life quite often, but we want to make them and define them scientifically and it related to kind of their importance as far as we discuss in science. So first of all, we have forces, right? That's a push or a pull on an object, and it changes the motion of the object. It has size and it has direction. So the way that we measure forces is using newtons. Now you might remember newtons from when we talked about weight. So we measure it with newtons. It's the SI unit of force. So that's going to be important as a label. Now we also have what's called the net force. So we combine all of the forces that act on an object. So if these two people are trying to move this piano, they are using different forces. The girl on the left here is using 25 newtons and the boy on the right is using 20. So if we add them together, they have a net force of 45 newtons to the right that they are, the force that they are putting on that piano. So if they act in the same direction, of course, which they are right now, then we add them together. But if they are not acting in the same direction, think of it as like a tug of war, right? So these two dogs, this one has 10 newtons of force moving to the left, and the one on the right has 12 newtons moving, of course, to the right. So in this case, they are moving in opposite directions. So we have to subtract the large from the small, and it gives us 2 newtons of force to the right. So this dog would be winning the tug of war at this point. So we have unbalanced forces, and this is a great example of it. So they produce a change in motion. They're not evened out, and if it's not zero, then obviously there's going to be a change in motion. So think about a soccer ball. It's going to move because a player is going to exert an unbalanced force on the ball when they kick it. And there's many, many examples that we could use of this. So that's the basics of forces. That's going to be important to what we're going to be doing. Now we want to talk about friction. So forces are affected by friction, clearly, and our everyday lives are definitely affected by friction. In fact, we couldn't play a lot of sports if we didn't have friction. So we're going to talk about that. Think about it in terms of speed and acceleration too. For example, we're going to talk about air resistance, which is what we call fluid friction, right? It's the force of the air. It's the friction of the air on cars or us as we move through it. So generally speaking, friction is a force that opposes motion between two surfaces that are touching. So simple example, we talk about forces and friction here. So there's a book sitting on a desk, right? And it's a larger book. In this case, the yellow one is larger than the red one. Think of it that way. And there's some type of a force. Maybe somebody's moving the book or trying to push it. So you can see the purple arrow here is going to overtake the yellow one, right? In this case, same thing, right? The force acting on the book is bigger, the arrow is bigger than the force of the friction. So obviously you're going to be able to pick up the book, right? So it says there's more friction between the book with more weight in the table than there would be between, obviously, the smaller book and the table. So you're going to need a harder push, right? A harder amount of force to move the yellow book than you would the red book. Okay, it's kind of like if there's a breeze moving through our classroom, it can easily move a piece of paper across a desk and the paper will fall to the floor. But it's probably not going to lift a book off the desk. So that's just another example. So turning a book on its edge doesn't change the amount of friction between the table and the book. That's important to note as well. So the friction is greatest between objects that are rough versus smooth. And I want you to think about that very importantly as we move forward. Think about trying to move something across a carpeted surface versus, let's say, a hardwood floor or a linoleum kind of floor like the ones that we would have in our hallways at school, or a ceramic tile floor versus carpet, or grass versus the sidewalk. I want you to really think about that as we move forward. So the friction between those surfaces that are rough versus smooth is going to make a difference. So I bet you could think of a lot of examples, right? If you ever had one of those wind-up cars when you were a kid, or maybe you still do, where you push it backwards to wind it up and it goes forward, it's going to go a lot farther perhaps on a wood floor versus carpet or something like that, okay? So there are several different types of friction that we want to address. We have what's called sliding and rolling. So obviously this would be between moving surfaces. So the amount would depend on how the surfaces move. Think about trying to move this piece of furniture if it doesn't have wheels on it, right? It's going to be pretty tricky sliding it across the floor. But if you put wheels on it like they did in this picture, or you put those scooters underneath it to move it, right? It's going to be so much easier to roll across that floor than it would if you're trying to drag it without wheels. Imagine going to the grocery store and not using a grocery cart with wheels. If you were just trying to drag that cart across the floor, what the difference would be. So it says moving a heavy piece of furniture in your room can be hard work because the force of the sliding, right? It's sliding across there. It's pretty large. Now, if you have rolling kinetic friction with wheels, it's going to be easier to overcome. So that's just the example there. Then we have what's called static, right? Not moving. So that would be the book sitting on your desk, right? So if you don't apply a force, there's no friction, right? But if you're applying a force, then you're going to have some friction going on, and they're showing you that. And obviously the greater the force, obviously there's more static friction. So it just gives you some examples there. So think of examples where friction is helpful, and you might want to think about that in terms of the winters in Wisconsin or in a sport that you play, okay? So obviously many examples. So think about hockey, for example. Why does the Zamboni come out in between periods? Think about if you ice skate just in general. Why do they clean the ice up? Think about curling in the Olympics. That's another sport where you want to have some friction. Think about gymnastics. Why do you put powder on your hands? Think about basketball, okay? Think about the ball that you use. It's not as smooth. There's ridges on it, right? So we could have a lot of conversations about where friction would be helpful or a problem. So in the wintertime, think about when the roads are icy. That means there's less friction. So what do, right? We put sand on the road to get friction. We even put salt on the sidewalk, which actually has two purposes, right? It helps us melt the ice, but it also creates friction for us to be able to stay upward. And so we also sometimes put like snow tires on that have chains on our tires, or more rivets on our tires that we want more friction. And so they obviously, would cause our gas mileage probably to change, and for the worse, but they help us grip the road. And sometimes people even put sand in their trunk to dump if they get stuck somewhere. So those are all examples of where we want friction, right, in our everyday lives. So it can be harmful, right, and it can be helpful. So there's ways that we limit it, which we mentioned, and there's ways that we actually, it causes problems where we don't want friction. So for example, we make cars so that they have a sleek shape so that they can cut through the air resistance, the fluid friction that we experience from the air. We don't typically have boxy cars like semis, right, that don't get reasonable gas mileage. So we talk about air resistance or aerodynamics when we talk about cars. We want them to be sleekly shaped so that we can be able to get through the air and not use a lot of gas to do so. So there's ways that we obviously would think of it as harmful or kind of wasteful, and there's ways that we want it. So those are all things I want you to think about as we move forward and study these labs that we're going to do. And finally, we're going to talk about gravity. So gravity is another force, and we kind of forget about it as well. But it's also helpful when we think about playing sports and such. So we talked about gravity a little bit when we talked about the gravitational pull and the differences between weight and mass on different planets and such. So we're going to review that a little. So it's a force of attraction between objects, and of course it's due to their mass. So when you think about the planet or the body that we're on, that's what we're kind of mentioning. So gravitational force pulls objects towards each other. That's why we are obviously sitting on Earth, or when we jump, we're pulled back to Earth. So compared to other objects around us, the Earth is huge as far as its mass. So this might be, or this is why objects aren't necessarily attracted to other small objects. They're more so attracted to the Earth. So the Earth's gravitational force pulls everything toward the center of the Earth. We know that, right? Now, that's why my pencil doesn't hit, obviously, like gravity doesn't pull it to my hand, right? It goes to the earth. So that's an important thing to note. So Isaac Newton, who we're going to study a little bit coming up, he realized that the same unbalanced force affected the motions of the apple and the moon. So again, he came up with some very important pieces to the scientific puzzle that we're going to study. And he really thought about gravity a lot before we knew a lot about it. It seems simple to us now. But there is a law of universal gravitation. So it shows us the relationship between gravitational force, mass, and distance. And so depending upon how far objects are apart and what their masses are, this affects gravity. And so Newton really studied that and came up with it. So here are his two rules, which should make sense to us, right? So gravitational force increases as mass increases. So we have the example of the elephant and the cat, which I'm using. So gravity between the elephant and the earth is more. And so the gravity between the cat and elephant obviously is not going to be as strong as the earth and the elephant. So that's why they are not attracted to each other like you or I or they are to the earth. So the gravity on the moon is way less than the earth. And we mentioned this, right? So there is gravity on the moon, even though some people say there is not. That's a misconception. But we weigh less on the moon because that body, the moon, is less massive than the earth. And so weight is a measure of gravitational pull. So this is a great picture which I want you to be familiar with. It says the gravitational force between objects increases as the masses of the objects increase. So the arrows show us the gravitational force. So look at these two smaller objects, right? So the gravitational force is small because they have small masses. Okay, think about the moon. Now, larger objects, right? If they're larger objects, then look at that gravitational force, right? It's going to be larger. So this is sort of a simulation of, maybe you could think of it as the moon and the earth. So the second part that we need to know is that gravitational force decreases as the distance increases. So same size objects, but look at how close they are. That gravitational force is going to be stronger. The farther apart they get, the less they are pulled back together. Now, this isn't a thing that could be measured with inches. We're talking significant distance. So when you think about that, make sure you're thinking of it in terms of not like tiny little space, right? So that's an important piece to remember. And then the big thing too that I think is always important to note is that Venus and Earth are about the same mass, all right? But Venus is closer to the sun. So the gravitational force between Venus and the sun is going to be greater than it is with the Earth and the sun. So that's an example of what we were just talking about, where we're talking significant distance, and that's important to note. So remember, just a quick reminder about weight. So it's a measure of gravitational force. It can change. It does change with the body or the planet you're on, and really depends on where you are in the universe. And we measure it in newtons. The SI unit for weight is Newton. And then mass, remember, it's the amount of matter in an object. That's not going to change. It stays constant no matter where you are. And remember, we measure it in grams and kilograms. So another simple example, which your book kind of explained here, is the astronaut. So if you look here, he's 1,588 newtons. Let me just move this for you so you can see it a little bit better. There we go. So here he is on a spring scale measuring the weight, right? So he's on Earth and he's 1,588 newtons. Now he's in space and he's 271 newtons down here. And then over here, look, he still has the same amount of mass. He's 162 kilograms. That's the amount of matter in him. It does not change whether he is on the moon or on the Earth. So this is just a quick review of kind of what we learned about in a little bit ago. But important to note when we're talking about forces, okay? That's it.